Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in California and the coordinator of the SERDP and ESTCP webinar series. It is my pleasure to facilitate today's webinar. Today's webinar focuses on DoD-funded research efforts to develop systems for analyzing operations data with the overall objective of improving performance and energy savings. We will have two speakers. First, Mr. Brian Clark will talk about fault detection and diagnostic technologies and their potential to provide cost savings and efficiency gains at DoD installations. Second, Mr. Brian Urban will talk about the use of automated fault detection and diagnostics for centralizing and streamlining mechanical faults in buildings, leading to both energy and cost savings. Both presentations will be followed by a brief Q&A session. The next two slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and also provided to you in your webinar registration confirmation email. If you cannot download Zoom, you can still view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have difficulties with the slides or if your screen freezes, just try keying Control and F5 to perform a hard refresh of your browser. And in case of continued difficulties, please download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. We'll go ahead and drop a link to the PDF of the slides that can be downloaded now. Another viewing option is to go to the SERDP and ESTCP YouTube channel at the link shown here, as we will be live streaming this webinar. A few reminders, today's broadcast will be listen only. You can submit questions using the Q&A box on your screen. Please do not wait until the Q&A period to submit your questions. We do encourage you to get them in well in advance of the Q&A sessions, which will take place after each presentation. We ask that when you submit your questions to add your organization name at the end of your question, so that we can identify you during the Q&A session. And finally, please do not submit questions in the chat box. Use the chat box for comments related to technical difficulties and the Q&A box for questions for the speakers. And with that, I'd like to introduce Mr. Timothy Tetreault, who is the ESTCP Program Manager for Installation Energy and Water. Before joining SERDP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused his work on energy efficiency and renewable energy project development, primarily for the federal sector. Tim, please proceed.
All right, thank you, Rula, and welcome everybody to today's SERDP ESTCP webinar. To start, I'm going to have a few slides to go over the programs, and then I'll hand it back to get into the presentations. The SERDP and ESTCP are the Department of Defense's investments in energy, environment, and installation energy science and technology. The programs report to the Deputy Assistant Secretary of Defense for Energy Resilience and Optimization, headquartered at the Pentagon. SERDP is the Strategic Environmental Research and Development Program established by Congress as a partnership between DoD, the Department of Energy, and the EPA. SERDP addresses high-priority environmental science and technology opportunities that focus on the top priority DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. And ESTCP is the Environmental Security Technology Certification Program, in which we demonstrate and validate innovative environmental and installation energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. Advances in science and technology provide the department with the tools needed to effectively manage and restore its assets to protect troops, their families, the public, and the environment. SERDP and ESTCP investments improve installation energy resilience, environmental cleanup, UXO remediation, resource conservation, and the sustainment and maintenance of defense assets. SERDP and ESTCP fund, monitor, and actively guide relevant and applied research, development, testing, and evaluation projects for DoD's top environmental installation energy challenges. Our programs currently fund over 600 active projects. To maximize research impact, SERDP and ESTCP collaborate with top talent across sectors. In 2023, we funded projects with 77 academic institutions, 91 federal performers, and 52 industry partners. Our innovation and technology development inform DoD policy and ultimately improve environmental and energy management. Our webinar series highlights outstanding projects across all our main focus areas. And you can find additional information about upcoming webinars at the link shown here. All past webinars are archived and can be accessed using the link. I'd like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. And we would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And at this point, I'd like to turn it back to Rula to introduce the speakers for today's presentations. And I hope you enjoy the presentations. Thank you.
Thank you so much, Tim. It is now my pleasure to introduce our first speaker today, Mr. Brian Clark, who is a mechanical engineer specializing in energy management at the U.S. Army Construction Engineering Research Lab in Champaign, Illinois. Brian serves as a principal and co-principal investigator for various ESTCP initiatives. His expertise encompasses facility system optimization, HVAC controls, and energy data analysis. Brian has been recognized for his dedication to energy management by receiving multiple Assistant Secretary of the Army awards, as well as awards from the Federal Energy Management Program. He received a master's degree in Sustainable Systems Engineering from the University of Wisconsin-Madison and is currently pursuing a doctoral degree in informatics with a focus on data analysis and information visualization. Brian, please get us started.
Yeah, thank you, Rula, and thank you, Tim. So as you heard, my name is Brian Clark at the U.S. Army Corps of Engineers Construction Laboratory, and I'm going to talk to you a little bit about our fault detection and diagnostics project, what FTD is, what we learned from it, and some of our recommendations for DoD's approach into adopting this series of technology. So I would start by asking those that are able to view the webinar to evaluate this picture and just react internally to what you see. So this is a typical view, what our building operators see as the primary day-to-day interface with their building energy systems. This is an air handling unit. It has a series of fans, coils, dampers, sensors, actuators. And what you see here are little pieces of data. And this is the data that runs the sequences of operation that tell the systems and equipment what to do. But because there's a lot of focus on raw data, there's a lot of puzzles to be solved here. So one of the ways that we became interested in fault detection and diagnostics was seeing that there were becoming more commercial tools available and recognizing that there's a better way to digest this information. Rula listed off a lot of professions and accolades I had to be sure were me as she was saying them, but one of my first jobs at the Army over 20 years ago was as a vehicle mechanic. So our focus with our team is really trying to not only help understand and optimize building energy systems, but really improve the quality of life for the people that are working on these buildings and trying to maintain them for resilience, energy efficiency, cost reduction. So we want to get away from the puzzle approach to providing data to these building operators and having a here you figure out approach. And one of the solutions for that can generally be termed fault detection and diagnostics. So I'll touch on a number of definitions in industry and elsewhere, but what we're moving forward with DoD is something close to what you see in the top bullet. That fault detection diagnostics can really be anything from a technology or a series of technologies or processes that provide some improvement in how detailed and actionable the information is compared to a typical building control or building automation system. So what we found is in order to really specify FDD on a given project, there's a number of classification features that need to be specified. So I'll go through these one by one in some subsequent slides. But first, I just wanted to highlight the project that we had funded by ESTCP in the Energy and Water Program. So at the Corps of Engineers, we don't have any vendor preferences. We're a government entity. So really what we're trying to do with this project is we wanted to broadly look at this technology, do a number of different multi-vendor evaluations, see how different people were doing different things with this technology, and answer a couple foundational questions. So we wanted to know, does FDD save energy? How much does it pay back? Will DoD use it? Meaning installation staff, building operators, technicians, energy managers, and do they like it? So these are the 4 factors that we had in our demonstration. We knew that there were some commercial statistics on these, some of these questions. We wanted to compare what it looked like in the DoD operating environment at our primary demonstration site. And as you can see here, we're pretty pleased with the results. So we didn't meet the 9% energy reduction that is sometimes used in the buildings industry for some of those commercial studies, but we got pretty close for our 7 primary buildings that we evaluated. We were under the 15-year simple payback that we were shooting for, although sometimes you might hear 2 years or under 5 years in a commercial setting. For the way that we implemented it, we were under 15 years, which means from a simple payback term for most ways that DoD gets funding on these types of building improvements. We were happy with that, so we passed that one. Measuring the implementation rate was a little tricky, but the way that we structured that reporting, we were much higher than our 20% issue correction goal, and we really found that people did like it. And if all the 3 other metrics above passed, but we didn't pass this one, it would have been really tough to make any recommendations on the affirmative coming out of this study. So I'm not going to read these slides, but I'm just going to go through them and hopefully make everyone aware that FDD has a lot of meanings. And even by FDD, sometimes, that may be AFDD, automated fault detection and diagnostics. It could be FDD and P, fault detection, diagnostics, and prognosis. Some national labs have really hit this on the commercial side, and Lawrence Berkeley National Lab, one of our partners in this area, uses the term EMIS, Energy Management Information Systems, where FDD is one subset, and you have things like energy information systems for metering dashboards and notifications, or even automated system optimization, where you're kind of given to some degree the keys to the castle for some smart system to make decisions on how to tune your building. We were really focused on the FDD. What are the primary data analytics tools that you could send data to, and you can get really high quality, prioritized, actionable information out of it. So ASHRAE has some resources here. There's not a ton of definition. There's more description about what FDD or AFDD is. There's been some research projects out of ASHRAE that have delved into this in some specific application areas, even going back 20 years before we really even had some advanced software and platforms that could support how we think of FDD today. There's some vendor-specific approaches to FDD and descriptions, as well as National Lab, other academic publications, and NIST has some kind of niche FDD scenarios like this air conditioning heat pump program that they have shown here. So really, we wanted to think about, well, how can we generally describe FDD? So if we're trying to procure FDD at the end of the day in DoD, we can get on the same page with what that means. So the first factor that we use is methodology. So we noticed that there are some folks in the academic and in the national lab circles that when they talk about FDD for buildings, they're really talking about something that's more on the left here, this white box or quantitative model-based approach to FDD, using energy modeling to build a representation of what the building should be doing under certain conditions, and then comparing actual conditions to that. I would say almost across the board for the vendor tools we see commercially available, and Brian Urban can probably expand on this, we see rules-based, we see algorithms. So some degree of sophistication that is doing a lot of if-then, but using more granular data or some kind of advanced combination of data to make that decision in a more, I would say, detailed way than a typical alarm on a building automation or control system. Another factor we look at, and this is one of the most important ones, especially as you're coordinating with cybersecurity or network management folks, is location. Where does the FDD live? And the answer is it really is a lot of places, or it could be a lot of places. So some vendors will start with FDD algorithms that live at the controller level. Some will put some kind of a piece of hardware or box or sometimes software at this higher level where the front end brain of the control system lives, this level 4 in this typical hierarchy diagram. And others, and what's really become very common and a direction that when we started this project right before COVID, we didn't see as much cloud computation as we do now. So there's been a big migration to have data analytics in the cloud, send data from a control system and from possibly other sources to a cloud location, whether it's on a government cloud or whether it's a commercial cloud, and we'll talk about those kind of implications. So what does the FDD need for data? So this is another question that has to be answered. It could be real-time data, or it could be historian data that a control system logs, or some kind of a cache puller will pull out, maybe as a BACnet object, for instance. But it can get kind of complicated. So in this study that I'm citing here, shown below, there's even multiple levels of the data collection. So there's a first pass in these different feedback loops where we're looking at aggregated annual energy data. And then from there, there's some key performance information from the control system with some different sampling times. And then they go into detail and they look at real data-driven, 15-minute type data that they're pulling here. So even one FDD implementation can pull data at different aggregations from different places, usually operational functional data like what a damper is doing, what this pump speed is, but also sometimes utility data, energy meters, water meters, and so forth. Functionality. So another metric, and probably one of the most crucial ones when you're trying to procure, is what do you want the system to do, or rather, what do you want the FDD to know? So this equation up top here is something that I wrote up to try to illustrate what something like an ASHRAE guideline 36 AFDD algorithm looks like, or fault condition. So like I said, there's different levels of sophistication. This is kind of a starting place that we can do something like, instead of look at a supply air temperature and say, is it meeting set point or not, like we would typically do with our alarms, there's a way to get slightly more elegance where you're looking over time. You're taking average conditions, you're adding some kind of reasonable thresholds for things like, in this case, fan heat. And there's some internal constants that have to be mapped out there, because we know that there's no perfect temperature sensor. And as we start running through these equations, we don't want to have more nuisance alarms for our building staff. So you could get 40 of these from certain vendors or platforms. You could get 4,000. So what we wanted to look for in DoD was probably not the Cadillac of fault conditions, but we wanted to be able to identify high priority ones that seem to be supported by most FDD providers. We've got a list of that to pull from kind of a la carte in some of our template information. System is another question. So, what are the levels that the FDD is operating at? Is it looking at certain components? Do we need to identify specific pieces of equipment in a building, as well as certain buildings? And then how are we aggregating some of those pieces of information? There's been some studies cited here that talk about key performance indicators that are missing in this aggregation chain. So identifying if you want to see certain things accumulated at certain levels, if you want to know what is the, oh boy, kW per 1,000 cubic feet per minute of supply air in all your buildings so you can compare them, those kind of KPIs would have to be conceived or discussed, procured, and so forth. And sophistication. So there really is a wide spectrum of like how smart the FDD could be. So starting in this pyramid of, the data to wisdom framework, right now we're really still in DoD working with data from these control systems, where if we have a zone temperature and a zone temperature set point in a space, what we're mainly doing right now is reacting to where we have a deviation from that set point. So if you get an alarm as a maintenance person, it's not super helpful just to be told you have a temperature that's different than your set point. As you go up that pyramid, we can get more helpful turning that data into information with things like a basic fault that might be something like, hey, we've been watching your fan coil unit valve position for the past 15 minutes, and based on your discharge air temperature sensor on the other end of that coil, it doesn't really seem like anything's happening that you want it to happen. So we don't know exactly what it is, but we're going to give you a list of possible diagnoses. It could be a clogged strainer, it could be a faulty valve, could be a pinhole leak, or it could be a faulty sensor. As we keep going up, we can get more and more advanced with systems that will deal with data gaps and impute different values to make sure those aggregations have meaning as they get rolled up, or even knowing how to filter when certain conditions don't have operating hours that you would want to count certain faults, and being more detailed with those diagnoses. I would say I'm not seeing a whole lot at the top of this kind of wisdom pyramid, but I can see where it's going is something that just continues to aggregate and put things into really bottom line information for executors and planners at our installations and beyond. So something that says some percentage of these fan coil units have experienced this fault this year. It's resulted in some number of dollars in work orders, and if we fix it, we get so many $1,000s in savings. We're going to issue a work priority. So that's kind of where we want to go. At the bottom is where we're really starting right now in DoD, and FDD is some combination from or some escape from just data. So even that second tier of information, I would say a lot of people would say that's a basic FDD fault that we can configure. Workflow is another important piece. So if you get everything right to this point in an FDD implementation, but you don't have anybody at the other end of it to use this system and respond to it, it's really a notification system. It's advanced in that it's telling you, not only here's a problem, but here's why that you have a problem and what you can do about it. But you need roles at an installation. So not every installation or building is necessarily ready for FDD, but there are a number of roles that we can look at to say, if you have this kind of staffing, you're probably in a good position to maybe add an FDD analyst or service contractor, or make do with the staff you have, although we really have seen a lot of success with having somebody that can say, sure, I know you're busy, you have the FDD to use and to make your own faults, but we're going to have a 1-hour call once a week or once every other week with your maintenance team and just say, here's the top 5 things we think you should be focused on this week. Interface is another question to ask. So how do you want to see and interact with this data? So usually there will be dashboards, certain reports like a plan efficiency report for that quarter, and certain notifications. Do you want them with your existing control system alarms, or do you want a completely separate source via email, via text? We focused a lot on the dashboard. So this is an example from one of the demonstration buildings, and it's certainly busy, but I think it's novel in the sense that in DoD, when we configure graphics for a control project, we don't have any level like this of a building summary. It's not in our criteria. And I think this is a very aspirational move to have these different types of faults. So the colors mean, is it a maintenance fault? Is it energy? Is it comfort? Is it critical? having some of these aggregated scores and checkboxes, these are the kind of snapshot views that we want to be able to provide our building operators. So what you see in the paragraph here is my attempt to kind of congeal some of those concepts, that there's different ways to classify FDD, and give an example to encourage that if you're thinking about an FDD implementation or talking to a vendor, or you are a vendor communicating with DoD, I would really encourage this, at least this level of detail, probably more than that, so you can communicate, I need these ports and protocols, and I have a microservices, SaaS. But really, at the very least, we need to know, we're assuming rules-based, where does the FDD live? Let's put it on a diagram. What kind of data do you need? How am I going to see it? Where are we going to apply it? And who is it for? So in addition to the demonstration site, we did a number of evaluations, mainly at our main campus in Champaign, Illinois. Happy to go into detail about some of these products and what some of the goals were. But we were able to connect on our DoD research network. We figured out what some of those processes were to write up in our implementation guidance. In general, learned a lot about what was common, what different names and processes were for different types of FDD features. So as part of our ESTCP project, we developed a quick start guide. So this was meant to be as a supplement to our 100 and some odd page final report, that we had a 10-page pamphlet of sorts that was a, hey, if you're interested in FDD as a DoD installation individual, that here's a roadmap of at least how to think about getting started. So if you're interested, here's some resources. Here's some way to think about selecting buildings. Here's the step where you got to kind of define what your functions and reports and features are that you want. And you can kind of see that that goes all the way, but at the right, there's always an escape hatch that says that, if this is too much for you, there's an FDD Lite solution we would recommend, and I'll touch on that in a moment. We made a number of templates. So really as an applied research entity within the Corps of Engineers, we really wanted this to be a rapid transition if we had good results with our demonstration. So one of the things that we packaged is the FDD procurement documents that we used. We want to make that available in some generalized forms to DoD. So we publish that, or we will publish that with our final report when it's approved. And one final thing to leave everybody with that we've been trying to standardize on. This is a diagram I made, blatantly ripped out of the field of psychology from Maslow's hierarchy. And I try to do this as a caution and as kind of a baselining of making sure we don't get the cart before the horse with things like FDD. And I would just say that the base physiological need of any building or control system is to make sure that things function. So you need power, maybe even backup power to some of these control system components and devices. They need to have inputs, outputs, and the inputs, typically your sensor infrastructure. We need that data coming in. It's got to be, moderately calibrated, and we got to have sequences running those controllers that make sense or can make sense enough that the data we get out of FDD would work. You need to, of course, secure those control systems. You'd ideally want to integrate them to a base-wide system or to a larger system that could send that data out. And that's where I really see FDD as kind of more towards this robust and optimized part of the self-actualized control system framework. Is once you get a functioning, secure, integrated control system that actually is being used and has the staff and the workflow, you just want to get more out of it. Now you're probably ready for FDD on your project. There's a whole cybersecurity conversation we could have, especially about these cloud connections. So I'll just kind of flash this up and let folks know that there's a FedRAMP certification piece that we're trying to help industry with and potentially host put out a solicitation of interest to see if anybody wants Sherrill to sponsor their FedRAMP certification at certain levels. But still, even if you get that authorization or certification, there's still a authority to operate set of changes that need to happen at the installation to support any connections or any configure changes for data going out, or even internal configuration changes like activating licenses and features that didn't exist when you got the authorization. And of course, the off-ramping here, and this is something that we published through our ERDIC library, was a expanded or enhanced building control system graphics set of criteria changes that we're coordinating with DoD to update our control system inspection criteria. This is what the typical graphic looks like. We know we can do better. So we made a number of designs and we said, if you can't do FDD, you can do FDD light. Make better use of your control system, use some basic faults, follow some information principles to make sure that we are following suit with the rest of the 21st century with web design and usability standards. And just to conclude, so we've tried to put our thumb down on what FDD is from a general sense and how to procure it. We had success with our demonstration projects. We had a lot of issues and lessons learned as well. You can read about in our reports. And a lot of our tech transfer includes the quick start guide, reports, FDD templates, the FDD Lite, which was really almost a separate off-ramping from this project that we coordinated through the specs and criteria program for the tri-services. So expect some changes there shortly. And we'd like to push forward some FDD criteria. I'm actually at an industry forum for control systems and cybersecurity within DoD this week and just presented on the FDD criteria updates that we'd like to see as a criteria change request. So rapid tech transfer, more to follow. So we saved energy. You could kind of put a rough number to what this would mean for DoD. Again, not every building is ready for FDD or would be an appropriate candidate, but if you just kind of use the rough numbers for the $5 billion or so that DoD spends in installation energy, if you could save 8% in every building, just as a rough order magnitude, you know, it's hundreds of millions of dollars of potential energy waste that could be addressed. But also there's that installation O&M piece, making their quality of life better, taking away the puzzle framework of this control system data and giving them actionable information. And as busy as they are, the fact that we got these highest scores on our satisfaction questionnaires is very promising that we're going in the right direction. Here's my contact information. Please feel free to reach out. Look forward to your questions. Thank you.
Great. Thank you, Brian, for a wonderful presentation. Just a reminder for our audience, please go ahead and submit questions using the Q&A box on your screen. We have received several questions on Brian's presentation, and we'll relay them to Brian right now. The first one is from Hussman Technologies. Are FDD data sets models available to support emerging proposals?
That's a great question. I've recently been made aware of some test data sets that Lawrence Berkeley National Lab has used. I could probably find the name here if I had a moment to Google, or we could follow up afterwards with you, but the short answer is yes. There are some standard data sets that emerged out of, I believe, an ASHRAE research project that a number of national labs and academic studies have used for these test purposes.
Wonderful, thank you. This next question has to do with costs. Can you elaborate on what types of implementation costs you incurred in your demonstration?
Sure, yeah, another great question. So one of the value or potential value with FDD is that there are some cases where you're adding predominantly software configuration labor with limited hardware, if any at all. So in our primary demonstration site, we didn't expect any hardware, just configuration changes at the controller level and at the front end level to make that data available and set up on our new dashboards. However, one of the surprises with our project was that the controls vendor at the installation level bid on it in a way that they wanted new pieces of hardware that were kind of duplicate controllers or routers because they were worried about capacity issues with how many points and the memory associated with running these additional algorithms. And they wanted to kind of can it off-site and keep it somewhat siloed from the more operationally important sequences of operation that were being ran. So we had, an additional probably 20,000 in hardware costs just for that purpose. But for 7 buildings, if you can read about it in the report, but we were somewhere in the area of $300,000 to implement at these, we started with 8 demonstration buildings. However, a lot of that was learning curve. A lot of that was these dashboard designs didn't exist, and the vendors knew that they'd have to put a considerable amount into that. So we tried to line item out some of those costs in our final report. But at the end of the day, we got under a 10-year payback, for a new start where everybody was learning. We were pretty happy with that.
Thank you. This next question is from Manhattan University. Could FDD be used for water supply systems within buildings? For example, building water distribution uses energy for pumping water treatment, water heater, etc. So can you use it for water supply systems?
I certainly don't see why not. I'd be really interested in Brian Urban's take on this, if there's any specific examples he can cite. But the way that we're looking at FDD from this DoD demonstration project standpoint is it's just a general term for data analytics for building control systems. I know that there are some more advanced things for, if you know the term SCADA and ICS for, wastewater processing facilities and other automation that's at that PLC level. But for our typical building control systems, if you have water meter data coming in, or you have any water quality sensors associated with those control systems, there's no reason, if you can think of a performance indicator and some kind of an algorithm that would tell you, what is my average acidity or level in this hydronic system over the course of a year, or alert me when for more than an hour I'm above this threshold, or what's my water usage baseline comparison for what I use this year to next. I think all those are on the table for FDD.
Wonderful. Thank you, Brian Clark. Brian Urban, would you like to weigh in?
Sure, yeah. So with the vendor that we demonstrated, they're called Symmetrics. They do work in process as well as energy systems. So if there is a rule that you can create, it doesn't take much effort to come up with some data-driven fault rules to analyze anything. So they do things in manufacturing processes, could be water plants, could be any sort of data that you can get on the network.
Great, thank you. All right, back to other questions that we've been getting. This next one is from Missouri Science and Technology. And if we can please go back to slide 24. On the slide, there is a block box, which refers usually to deep learning models. Can you discuss what the adjacent gray box represents? Does it refer to something related to semi-supervised learning?
Sure, yeah. I will do my best with this, although I'm not the author of this diagram. However, my understanding of the gray box modeling is that it's a combination of black box and white box. That's the gray. So if white box modeling is more physics-based, meaning that we know the equations in use, we may use energy modeling like Energy Plus or eQuest, but those are very physics-based. You know what's happening in the computational portion of that model. Black box, my understanding is more on what we would think of the machine learning side. So we may be training a model based on inputs we're giving it, and we may understand the machine learning or neural network processes in the middle, but we're not really constraining that model to any actual physics. Data is going in, and we're getting a model set of outputs and characteristics coming out. Gray box is some kind of combination of that. I haven't seen any of this in use or being studied. Somebody is welcome to provide an example if they've seen any, but I can imagine an example is where you are largely using physics-based modeling, and you're using some of those statistics associated with that model to then feed into a machine learning algorithm or set of algorithms in some kind of a network to build an enhanced model would be my best guess.
Wonderful. Thank you for a very comprehensive response. This next question has to do with naming conventions. How do you handle, or how did you handle inconsistent point naming conventions?
That is a great question, and it gets to the crux of so much of the challenges with FDD is for an existing building, and especially an installation of buildings built by at different times by different people, managed in different ways. You get all kind of point names, and as you roll those up to an installation level, it can be very difficult to make sense of the data that you're seeing. So I would say that what the FDD community has done has made a lot of progress into different metadata approaches. So how can we use different tagging approaches? Like you could look up Haystack is one, brick schema is another. Some front-end systems like Niagara have their own tagging natively or with the analytics licenses. And that is meant to ease that process, that if you have different names for similar points, that it's going to catch a lot of those. However, what we experienced is that there's a lot of hierarchical relationships with these points that I think Brick does a good job, but at the end of the day, if you don't have any context for what the points are doing in relation to one another, and you don't have a model that's catching these things, we had some FDD that we were being reported like, oh, there's a pressure issue here. But what the FDD didn't know is that there was really an arrangement of several pumps, some in parallel, some in series. And what it was looking at for pressure in one place of the system, it needed to take into context the operation from elsewhere, given the interrelated nature. So that can get very difficult. Point names are very important. We push that standard really hard in the DoD, but it's going to be a challenge. Metadata helps.
Thank you so much. This next question has to do with the FedRAMP approval process. Can you talk a little bit more about how this approval process for FDD tools? Can you elaborate on the process? You sort of alluded to it. Can you please provide additional details?
Yeah, sure. I'll do my best. I'm not a cyber person. I'm cyber adjacent, which means I'm really an operations person that has had to sift through a lot of cybersecurity requirements that have changed and accumulated over the years. So FedRAMP is a federal process. If any federal data is existing on a commercial cloud, there was an act recently that kind of codified FedRAMP. I think it was the National Defense Authorization Act, saying that FedRAMP is the authoritative standard approach to do the security assessment and authorization for any of this commercial cloud computing. It's specific to unclassified federal info, so it's not that you could put any old federal data on there. But some people think of this as like the RMF for cloud. I think there's some overlap and there's not direct parallels. But like RMF, you have to establish an impact level. What's the nature of the data that we're handling? How confidential is it? What would happen if someone got a hold of it? What would happen if it was processed incorrectly? The issue that we're seeing, if FedRAMP has, you can go to the FedRAMP website. We've got some kind of links in our final reports, but there's a marketplace that if a commercial cloud offering gets approved at these different levels, they become available on the marketplace, is my understanding. To date, I haven't seen really any building operations existing on that marketplace, although things are moving fast, and I know there's probably a number that are maybe being processed right now. So we're hoping to put out a solicitation of interest that if there's a multi-vendor FedRAMP certification that we can host at our controls test lab at Searle, we know that there's no individual project that will likely take the cost of getting the certification, which my understanding is that it could take years. There's a non-trivial amount of money that would need to be kind of put into it to document and test and get validated and configure and risk manage those pieces. But the main thing I would want to say too is, you can look into the FedRAMP requirements. There is there's a program management office, so PMO, which means that they're there to help you. So if you contact the PMO with any questions, they'll show you, some documentation, show you the templates that they have to help you get through that FedRAMP process. But we want to help make these tools available so that we can have open procurement on FDD services and platforms.
Great, thank you so much for that, Brian. Which specific FDD vendors did you assess as part of your project's additional evaluation?
Yeah, sure. We started with, gosh, I want to say 20 or so, 20 plus at the time in FY20 that we were aware of that seemed to have commercial products available for use in DoD. We selected project sites and tried to work with the local folks to see what was the best fit. So we had 3 initial sites, and because we were looking at Fort Leavenworth and they were an automated logic or ALC site, we used the ALC version of AFDD, which they sometimes call the QMA pages, the qualified maintenance action dashboards and sets of AFDD algorithms from their library. We used Niagara Analytics, the 2.0 library, which was available with N4, and some custom libraries once you purchase the analytics licenses and use some of those reports and dashboards and web views that open up. We wanted to look at Johnson Controls OpenBlue. We couldn't get the cybersecurity approval at the site, so we pulled that into our lab evaluation, as well as looking at Cimetrix Analytica that Brian's gonna, I believe, talk about, and CopperTree, and Kaizen, and Sky Foundry, SkySpark. A number of other ones that we partnered with Dewberry to pay to do some evaluation, like let's put into some tables. What are their cost models? What protocols do they support? How long have they been in business? We try to develop some of that information. Some of it may be outdated at this point, so we have some caveats in our final report, but you can find their assessments once that's published.
Wonderful. And one last question for you before we go ahead and transition to our second presentation today. Are there technology limitations in what architecture or protocols that are in use?
Not effectively. I would just say it will likely affect the cost associated with an FDD implementation. So I would say the more open, the better. We had sites that used some combination of flat Lawnworks as the protocol, other ones that were BACnet only, some that were ArcNet, and still others that had a Niagara overlay on top of some of those protocols. I think Niagara is fantastic in that it seems like a lot of FDD vendors seem to be very ready to pull BACnet objects off of those Niagara supervisory framework devices, the JACEs. Even if you have a lawn field network or a Modbus field network, you can still export those objects as BACnet objects. Makes it very easy. Or some folks will accept a historian export. So all your trends that you might be saving in a JACE and pushing up to your front end, you can push them up to their front end in the cloud, which is a nice hardware software free solution. However, we did evaluate things like Lawnworks, which is more of a protocol going away. A lot of folks have said, yeah, we've made our own tools and it's a little bit more work, so you might see a price hike there. But I see that as more of a cost implementation hassle than a lack of compatibility of support possible with what I see in DoD buildings.
Wonderful. Well, thank you again for a great presentation and for a very engaging Q&A session. At this point, we're going to go ahead. Yes?
Hi, sorry for interrupting. This is Tim. I just wanted to make a quick comment before we go on to the next presentation, if that's okay.
Absolutely, please.
I want to commend Brian on his work, his and his team's work on this project. They started just as COVID kind of impacted our ecosystem and DoD, and worked through that, attended to some of the delays that it caused, but also ended up with some really great work. And like we mentioned at the beginning of the introduction, our intent with these demonstrations is to ultimately transition the findings. And Brian is, at the moment, working on updating the UFC accordingly with some of the findings. So I wanted to commend him on this work and appreciate that effort. Thanks.
Thank you so much, Tim.
Appreciate that.
Yeah. And thank you again, Brian. Again, superb presentation. All right, well, we're going to go ahead and transition to our second presentation and last presentation today. Mr. Brian Urban will be our presenter. He is a senior engineer at Fraunhofer USA Center for Manufacturing Innovation in Boston. Brian has served as principal investigator on multiple ESTCP energy and water projects related to buildings, HVAC controls, energy systems, and cybersecurity since 2015. And from 2018 to 2024, he led a validation project of a commercial HVAC analytics platform and service for automated fault detection and diagnostics. And then in 2023, he led an award-winning project on validation of a wireless lighting controls retrofit for high-bay DoD applications. Brian received a bachelor's degree in mechanical engineering from Cornell and a master's degree also in mechanical engineering from MIT. Brian, we're delighted to have you. Please start your presentation.
Thank you. Hello, everyone. My name is Brian Urban. I'm a senior engineer with Fraunhofer USA. We're a nonprofit R&D company up in Boston, and we led an evaluation of the Cimetrix Analytica fault detection and analytics platform at 2 DoD installations. So this is a good segue after Brian's great presentation on sort of the range of FDD technologies and the need. We're going to talk about one specific vendor and our experience deploying that at 2 DoD installations. Cimetrix has been working in this area for over 20 years in fault detection, and they primarily serve commercial and institutional customers. So healthcare, pharmaceutical, hospitals, and universities, which have large campuses with many buildings and centralized building automation systems that aren't too different from how the DoD operates its own buildings. So the point of this demonstration was to show how this technology could work for the DoD and then figure out some of the challenges and opportunities that go with that. So just to start, for the overview, we're going to talk about HVAC analytics, but also analytics as a service. So not only does Cimetrix offer a tool and capability, but they also provide basically a consulting service to help the teams address the different opportunities that are identified, and we'll show how that's important for the DoD. The second piece is covering how we got connected. So if you've never done a fault detection project before, you might not be familiar with the process of what it takes to get the data, analyze the data, and make sense of it. So we'll go through that. Finding the faults, once you have the data, what can you detect? We'll go through some examples, and then we'll talk about how to actually turn those faults into savings. If you don't do anything with the data or the results, it's kind of a big waste of time. So we'll show how we were able to achieve savings in both of our installations. So the main idea or the main focus of this project was on HVAC-related energy waste. As Brian mentioned before, there's hundreds of millions of dollars of energy waste in HVAC systems. You hear rules of thumb of about 15 to 20% of HVAC end uses waste due to misconfigured controls. It could be bad sensors, could be mechanical equipment that's degrading. There's a whole range of reasons why systems don't work as they're anticipated. But the real key is that we're talking about hidden faults. So, I mean, everybody's used to seeing the alarm systems that go off on these controls systems. But those are pretty basic things like, oh, the chiller's down, the boiler's down, you get a service call. Those are obvious, but a lot of the energy waste comes from hidden faults, things you would never know are happening behind the scenes. And we'll get into some of the examples. There are ways to address some of this that are effective. We talked about retro commissioning, where you send teams in to look at the data and tune up buildings as a one-time activity. Those can be very effective, but they're hard to scale. And then once the systems are tuned up, they can start degrading again right afterwards. So that's one opportunity. But the other challenge is that facilities teams are way too busy putting out fires. They're trying to keep the systems running, answering the service calls or the complaints that this building is too hot or too cold or the boiler's down. They don't have time to go looking for energy waste, even if they had the data and the tools. So that's kind of the context of where the industry and especially the DoD is right now. Fault detection tools and automated fault detection can scale, but it's underutilized. And some of the DoD specific barriers have to do with the skill set of the people in the facilities teams, limited resource, not enough people, no money to fix the problems, getting access to the data, and then DoD's special cybersecurity challenges. So those are all topics that we addressed in the course of this demonstration. I want to spend some time talking about this particular technology and how it's delivered. So number one in the top, the status quo is DoD has a range of building controls networks that are collecting or storing or have access to untapped data resources. So they're generating data from endpoints like sensors, fans, pumps, motors, meters, control signals, all of the different information that comes in those operational networks. And they feed HVAC controllers, building automation systems, SCADA systems, your boilers, your central plants, a whole range of equipment. And so all this data is out there. It's getting secured. DoD is pursuing cybersecurity for all these control systems networks, but the data is largely underutilized, except for those limited dashboards that you saw in the previous presentation. So that's where we are now. And the idea is to take advantage of all that data to make some sense out of it. Cimetrix uses a proprietary device. They call it a cache polar. It's a small piece of hardware that collects data directly from the control system's endpoints. So you would typically install one of these boxes on the central network, and it would be able to talk to the controllers in all the different buildings on the campus. So it doesn't matter what protocol, they could talk to BACnet, LawnWorks, Modbus, or the vendor. They're not integrating with the control system front end. They're just pulling the data right from the endpoints. So it's interoperable, and it's an easy, effective way to get the data from the system. We're also pursuing a cybersecurity authorization for that piece of hardware right now, and we're, I think, at the 95% level. We're pretty close. So that would make it possible to reuse this hardware at other installations to collect data. That's for the hardware piece only. It doesn't control anything, so it's just collecting the data. The next step, step three, you push the data from the cache polar to an analytics engine. And so this is where you have a database, it stores the data, and then it models the system components in your buildings, in your systems, and identifies faults down to the root cause. Cimetrix uses a rules-based fault detection primarily. And so this is a commercial offering that they have. And for this project, we ported that commercial cloud to an AWS Gov Cloud to meet some of the DoD's cybersecurity requirements. That also would need an ATO, and we're pursuing follow-on efforts that would potentially address some of those challenges as well. Okay, so now you have the data, you have detected some faults. What do you do with that? In step 4, you have a user portal where users can log in, track the issues. You'll get a big list of all the things that are potentially wrong in the building. You can filter those issues, you can sort through them, and when you click on any one of those issues, you'll get a separate page that gets into the detailed diagnostics, what's the evidence, what happened, and what are the potential fixes for those issues. So this is where the day-to-day work happens. But Cimetrix learned doing this for many years that even a lot of their customers didn't have time or the skills to actually log in and use the tools. So because of that, they developed a service model where they have expert analysts that actually use their own tools to curate the issues and kind of find out what are the priority issues and then walk the facilities teams through the resolution. So having weekly calls, working directly with the teams to address targeted issues and get those issues fixed. So it's kind of a soup to nuts approach to finding the issues, getting the data, and then getting things fixed. And so in this presentation, we'll go through some examples of all of that. And and continue on. But we're going to start with how you get connected. What does it take to get set up and get the data and all that? So it starts with conversations with the facilities teams. Symmetrics has facility information forms, collecting basic information about the buildings that you want to onboard, getting building systems, architectures, meters, and priorities. They ask for the points and protocols to make sure they can get the data off the network. And they also request a building automation system points list export, and they can help the teams run the commands that would generate those reports. And so then they'll get an idea of what data is available and then how to configure that data in the next step. It's also helpful, but not necessary, to get documents like mechanical schedules, balancing reports, historical energy data, or as-built diagrams. Any of that stuff can help with the configuration effort, but it's not strictly necessary. The more information you have, the better the analytics will perform out of the gate, but all of that stuff can be updated along the way. Okay, so now that we know about the buildings, we're going to go on site and connect the cache polar. So we did a site visit at each location, and in about half a day, we got this device connected and talking to the different buildings. It really required only 2 steps in addition to plugging into the network. We had to add the IP address to some allow lists to enable the device to talk to different buildings on the network. And we had to make certain building automation system points network visible if they were not already. So this did not require any effort from the controls vendors or any special integration. Once they had access to the networks, that's really all that was required. In addition, once it's connected, Symmetrics would initiate a scrape. And this scrape would basically reach out to all of the visible endpoints and get whatever information they're able to provide. So you would be able to compare the scrape list with your building automation system export list and see what points are missing, or make sure you're able to talk to all the points that you need. So that's the first step in the configuration. Again, a half a day on site to get connected. Sometimes Symmetrics will actually ship this box to their customers. They'll plug it in. They won't even have to go on site. So it can be very efficient to get connected and start getting data. All right, once you're connected, Symmetrics does the work to get this configured. So different analytics providers, this can be a pain point. It can be very difficult for some of the vendors to make sense of the data and get all this talking the right way. Symmetrics has been doing this a long time, so they have some internal tools for doing this. But you start by selecting what buildings you want to get the data from and picking the endpoints. Typically, they'll exclude certain points like nuisance alarms or other things that they're not going to use in the analytics. But once they have that list, they'll have to map the points. There was a question earlier about naming conventions. Symmetrics has automated tools to do 80% of the naming, and then there'll be like a 20% manual effort to clean it up after the fact. And then the next step would be to define a topology, and that's really just a fancy word for what points come in what sequence. If you're in an air handler, is the cooling coil upstream or downstream of the heating coil, things like that. So they can set up point relationships, which basically feed into the model. So once you have the points are mapped and the topology is defined, you can initiate polling. So they'll have a database, and then they'll start storing data for all of the endpoints on the network every 15 minutes. And you can fine tune that. So if you have certain points you want to do micro trends or go faster than that, you can adjust those polling frequencies. And then they'll do a data review and make corrections on an ongoing process. So again, most of this work is done by the analytics vendor and not the facilities team. So if you have busy facilities people, they really don't need to do a lot to help get this configured. So for the 2 sites, we worked with Marine Corps Air Station Beaufort and Hanscom Air Force Base. And initially we were aiming to get about 12 buildings for the pilot. So we started with about 12 buildings. And then both installations asked if Symmetrics could do the whole campus. And so they went for it. And we got over 60 buildings polling right now, including a central chiller plant at Hanscom, and polling over 25,000 points at each site. So lots of data coming in and very efficient and effective to get this deployed at scale, again, without needing to involve the controls vendors at the different sites. We're getting data from over 100 different point types, temperatures, humidities, energy, power, all kinds of different data sources. And right out of the gate, we detected thousands of issues at both sites. Not all of those are important issues, but nevertheless, a lot of opportunities to fix things. There were 2 different controls vendors at the site. We wanted to show capability across vendors. So automated logic at Beaufort and Johnson Controls at Hanscom. The point naming quality was a bit different at the sites. Beaufort had probably the top 1% that Symmetrics has ever seen in terms of clean point naming. The team there was really experienced and probably top tier, very, I guess, unusual for the DoD or even the commercial sector. But then Hanscom Air Force Base was more typical for of their usual customers, where there's a mix of new and old systems and different naming conventions. But it didn't matter. The config effort for both sites was around 100, 130 hours in total, and that's almost entirely the analytics vendor. Probably less than 10% of that would be time spent by the facilities teams answering some questions. So very scalable to get the data, to make sense of it, and to get it ready to use for analytics. Okay, now that we have the data and we're starting to find faults, it's time to get to work. So as we mentioned before, Symmetrics delivers their service on weekly or biweekly calls with the facilities teams. So for about a year and a half, we had ongoing calls over Teams where a Symmetrics analyst would go through the list of issues, curate the top 5 or 6, and then we would have interactive diagnostics on the calls. So we would pull up an issue on the portal and explain what we think is going on. And then the facilities engineer on the other end at the installation would pull up their building automation system front end, pull up the same points or the same air handler, or take a look and either confirm or deny the issue. And then we could even do functional testing in real time, like cycling a valve and looking how the temperatures respond. A lot of cases, we were able to apply fixes in real time. So if there was a controller that was not working right, or a schedule that was incorrect, they could recognize that and fix it on the spot. So again, with a very limited amount of time, 1 hour a week, we were able to drive a lot of the savings. In some cases, they had to issue work orders to send someone out, send a technician out to take a look at a sensor in the field or make an adjustment. And then we would come back to it the week after or in a couple of weeks and see if the problem had been resolved or take a next step. But it's really, having a routine, getting into a rhythm, getting to know the facilities teams was really key to making, big strides in some of these issues and getting things actually fixed. We talked about workflow. Brian talked about workflow in the last presentation. Basically, you want to start by picking a good issue. So with a list of 1,000 things, you don't want to be focused on issues that don't have much savings opportunities. The next step is to verify that the issue is actually real and occurring. So there's ways to filter on issues that are happening now or only recently. So if you send a tech in the field, they'll be able to see that the issue is actually happening and help troubleshoot it. You don't want to waste people's time. Then you can promote the issue in the system, assign it a tracking number, and then start to investigate the root cause, add notes to it, attempt to fix, verify that it's fixed. And then Symmetrics would calculate energy savings. They have energy models that use weather data, real operational data to calculate estimated savings for the major faults that they identify. And then you close the issue and repeat the process. So that's kind of the workflow. And now we'll talk about some of the actual issues that we found. These are just a flavor of some of the examples. The first thing we found at Air Station Beaufort was about a dozen CO2 sensors that were reading very low. Something was wrong and they were reading close to 0. So they got that fixed, and you can see at the top of that graph that they're reading a normal value after that. But that can affect ventilation rates, indoor air quality, waste energy, and cause other kinds of problems. So that's an easy one. Detecting bad sensors like humidity sensors can impact cooling energy, mold growth, indoor air quality and comfort, a range of things. So that, again, just an example of very easy, simple algorithms to detect high readings or unusual readings that can affect operations. The next one has to do with equipment that runs when it's not supposed to. This is probably one of the biggest energy savings opportunities across the board. Equipment gets left on all the time for a whole range of reasons. Someone could be working on equipment and have it in an override and forget to release the override. This happens all the time. And so this is an example. If you look at the right, it's the occupancy command for the building. So it's supposed to be on a daytime, nighttime schedule. and on the left, you see the status of that same piece of equipment. So at some point along the way, it started to run 24 hours a day, 7 days a week. And so you can detect those sort of things and then get that corrected. But those issues don't get called in as complaints typically because the buildings are comfortable. Nobody's going to notice if it's running overnight and keeping the building on. So these faults could go on for years at a time and waste energy continuously, and they're pretty easy to catch and fix. So for each of these cases, it could be a couple $1,000s a year in energy savings opportunity, depending on the equipment, how big it is, what fans, et cetera. But those are really, really common and really big opportunities. Similar and related to that is command and status mismatch. So this would be a case where the unit is commanded to be on or off, and its status doesn't agree with that. And so in this case, it could be an in-hand override. The system will predict or estimate what are the possible faults, and then it shows you the fault rules that were flagged. So here there was a mismatch on air handler 3 and a supply air fan. So you could see all the different times that it occurred. Those orange bars each correspond to a time when that fault was occurring. So over that span of time, if you click on any of those orange bars, it will bring up the data related to that flag. So it's very simple to understand the logic of what caused the flag, and then you can go investigate the data on the control system. In this case, if it's a big system, if it's running when it should be commanded off, you could save 50 grand a year for this particular fault. So huge opportunity and often very simple to fix. Another one is when heating systems fight with cooling systems. So here you might have a zone that feels comfortable, but it's heating and cooling at the same time. So on the top, there's an example where a heating coil valve was not closing all the way, or leaking fluid or passing fluid when it was closed. So as a result, you have to heat and cool at the same time to maintain temperature in the zone. Again, nobody would report a fault, but if you can see that happening from the control system, you could potentially resolve tons of energy waste. Replacing that valve could save about 40 grand a year. And on the bottom, it's another example where a preheat and a chilled water valve were opening at the same time for a certain amount of the time. And so again, you're heating and cooling at the same time and wasting potentially $1,000 a year each time that happens. So again, things you would never detect, nobody would report it, but are wasting energy behind the scenes. Another example, this isn't really a fault, but it's more of an optimization issue. So this was a gymnasium. They had a whole bunch of VAV boxes, and a lot of older buildings in particular may have been commissioned with higher than necessary airflow rates or minimum airflow rates. The building codes have changed over time, and so that you might be moving too much air. So in a case where the set point is met, you might be able to dial back the minimum airflows. So in this case, there was a number of these VAV boxes, and working with the facilities team, we reduced the minimum airflows while keeping the temperature set points the same, and we got a reduction in airflow, maintained set point, and saved probably 5 grand a year per building in those applications. So ways to use the data to optimize equipment and performance is another use case that we looked at. Another one, again, this may or may not affect energy use, but it can affect operations. Compressor short cycling is a common fault that might happen. On the left, you see a 4-stage compressor operation where the compressors kind of take turns and share the load. They run for a couple hours at a time and then cycle off. On the right, we found some short cycling due to faulty control logic. And so here the compressors were coming on and off for a minute or two at a time, which is really bad for compressor lifetime. It can shorten the lifespan and cause compressor failure. This site actually had some compressor failures in the year before, and it cost 20 to 50K to get them replaced. So if you can detect this and prevent it, you can avoid costly repairs on your equipment. In this case, we were not able to fix the problem because it wasn't part of the facilities control system. It was part of the logic that was built into the chiller unit, and that was controlling the compressors. So in those cases, you can work with the vendor directly, let them know next time they're on site to tweak the logic, or if you have warranty claims or otherwise, you can work to provide the data or the evidence that there's some problem with their system. So another example of a different kind of use case. In some cases, the people on site don't have the tools or the skills to make the changes to the control system, especially when it involves detailed logic changes to the controls. Some vendors have proprietary software that you need to get access to make those changes. And in those cases, you can buy blocks of time from the controls vendors and give them a punch list. So you could bring them on site for a couple of days and have them start working from the top of the list down. So we put together packages like this for Hanscom Air Force Base, and they're trying to turn this now into a project to get someone on site to help resolve these problems. In addition, Symmetrics sometimes works directly with the controls vendors to get these items resolved when the facilities teams don't have enough personnel or time available to get those things done. So it's a way to kind of push the issue and get things fixed. So that's kind of an overview of the sort of problems that we saw. Just to wrap up with a few conclusions, the analytics that we demonstrated can deliver big energy savings and operational savings at scale for the DoD. Analytics as a service can make busy facilities teams even more effective. And analytics can support a lot more than just energy savings. So we talked about operational savings, indoor air quality, and then there's other applications like first-time commissioning of new construction buildings. You can use the data and analytics to help with that as well. So a range of different applications that could help facilities teams. As far as benefits to the DoD, these are some example issue counts from Hanscom Air Force Base. Again, we found thousands of issues. Over the year, we really drilled into about 60 or so at Hanscom, and most of them were related to occupancy and schedule. That's where the big opportunities were. Some simultaneous heating and cooling, economizer logic, and actuators, valves, and dampers that were misbehaving. Altogether, we found about $500,000 in savings opportunities at Hanscom. And in the span of about a year and a half, we realized about half of those. So very effective working with the teams on a very lightweight basis. We were able to drive some of these savings and get results. So I want to thank a few folks on the team, especially our host sites, Hanscom and Beaufort. They did a great job. A lot of other people not listed here did a great job making this project successful. Symmetrics did a great job as the analytics vendor, getting the data, working through COVID, and getting all the results. And then especially our cybersecurity support. So if you're going to do any of this, you need to involve the cyber teams early on. We worked with RMC because they were doing the ATO package for the control systems at Beaufort, and they were able to basically get us across the finish line for the ATO on the cache polar. So we're excited about that. We think there's opportunities to scale this at the DoD and repeat this in other locations. And so if there are some opportunities, or if you're interested in this technology, we want to hear from you. We want to know how this might help you at your installations, and we'd love to get your questions and input. So thanks so much for your time and attention, and be happy to take some questions.
Great, thank you so much, Ryan. Very clear presentation. We do have some questions for you. Did you have to install any new sensors to collect enough data for the analytics?
Yeah, so that's a good question. So yeah, it's some vendors or some analytics tools have to install sensors or get more data in order to do analytics. In our case, the only hardware that we installed was the cache polar device. Everything was already being collected, all the data we needed to do any of the analytics. And to build on that, Symmetrics, the way their fault detection rules work, their algorithms look for data sufficiency. So if they have an algorithm or a fault rule, it has a certain required number of data points that are necessary to run the rule. If those data points exist, the rule will run automatically. There's no extra configuration. If it sees enough points in an air handler, it will run the air handler fault rules that involve those points. So it's very much automatic, and it wasn't necessary to involve any other or install any other sensors.
Thank you so much, Brian. Did you need to work with the existing controls vendor to make the technology work?
Yeah, so some of the technologies or some of the fault detection vendors do integrate directly with the control system's head end, and then you have to integrate with them and maybe buy software licenses or have them involved in the process. For our pilots at both installations, we did not need to do anything with the existing controls vendor. All we needed to do was work with the facilities team to get permission to connect this box to the network. And then once that was done, the data was read directly from the endpoints. So they didn't have to integrate with the front end. We heard examples of cases where one of our host sites worked with a different vendor at one time, and they were unable to get at the data. They actually had to manually export the data every week or every month and send them CSV files and set up microtrans. And they said it was a huge headache. So being able to just connect a box and get the data was a huge advantage.
Great, thank you. This next question is from the Missouri Science and Technology University. Other than HVAC, has there been any work done related to power consumption and quality in buildings?
Power consumption and quality in buildings. Yeah. So the focus of this project was on HVAC and analytics, but Symmetrics and other vendors do look at power quality, power factor, load management. They can do building level energy benchmarking. A lot of the tools that you would see on their portal are customizable, so you can create graphs or views or dashboards that suit your needs. So there's a lot of opportunities there. They even have a utility metering part of their site, which we looked at a little bit, but basically any of the data points that are on the control systems network, they can automatically start polling. So we were getting a lot of smart meter data from the buildings at the building level, but also at the circuit or panel level in the cases where there was data for those things. So I know the DoD has a lot of energy reporting requirements, and a lot of the facilities people spend a couple of days a month running around reading meters and putting together spreadsheet reports to report on building energy use, for example. Some of that could be automated with tools like this when you have access to data centrally. So it really depends on what data is available or what you're looking to do, but that's certainly a possibility.
Thank you. Can you tell us if this technology worked if this technology worked in buildings? Sorry, let me rephrase that. Could this technology work in buildings that are not yet on a controlled system network, or is it limited?
Yeah, so that's actually a really good question. It works on both, actually. And so before we did this project, Symmetrics did a commissioning project with the Marine Corps at Camp Lejeune. They had a bad hurricane, and they were recommissioning a lot of their buildings. At the time, they did not have a central building automation network, so they actually went around and had cache pollers installed at each building. They would collect the data for a couple of weeks, and then they would go out and collect those boxes and then download the data. So it's not efficient. It's hard to scale that way, but it is possible to install these boxes at each building and collect data manually or do it otherwise. In addition, at Hanscom, we had a couple of buildings that were not on the central network. And so we were able to install cache pollers in those particular buildings just to get some data from those as well. So it doesn't have to be networked. It definitely helps and would make it more efficient, but it's not necessary.
That's really good to know. Thank you so much for that response. This next question has to do with the system's ability to read other data on the control systems network. Can you talk a little bit more about that and how that could be useful?
Right. Yeah. And so that's kind of what we were alluding to before. If the data is available on the network, and a lot of this is over BACnet or whatever protocols exist, if the other sensors are on the network, Symmetrics can probably read it. So again, we were getting data from power meters. It could be water meters. It could be any kind of operational data or command signals that are available. It could be alarms. We had a request from some installations wondering if we could use this as a secondary alarm system to provide alerts. Symmetrics isn't an alarm company, and so they wouldn't be able to guarantee to report alerts on alarms fast enough, but they would pick it up every 15 minutes when they do their scans. So it is possible to use this for other applications, but I would say probably not for instantaneous response use cases.
Great, thank you so much. And maybe a final question for you before we wrap up. What is truly needed for this technology to scale more widely within the DoD?
Yeah, so that's another great question. And so I think we've shown the value in a couple of installations, and we're looking at ways to, number one, complete the ATO for the cybersecurity piece for the cache polar. We're pretty close to that, and we think that'll make that available for more wide use cases just to collect the data from these networks. The second step is really getting the authorization on the cloud piece. And so again, Symmetrics has ported to a GovCloud, and there's some additional steps to go through this FedRAMP approval process. And so that's another key step. And then finding the installation partners who see the value in demonstrating this. We're pursuing opportunities to demonstrate a center of excellence model where we would have basically central groups within the DoD that could run the analytics or manage the analytics for groups of installations. So it would be like a support team or a Tiger team that could help a range of installations with their fault detection, diagnostics, and fault resolution at more of an enterprise scale. So instead of one installation at a time, it could be groups or regions where you get centralized support to help the installations as they need it. So we see that as kind of a future model to deliver this. But I think there's a lot of opportunities to start using this right now.
Great. Thank you so much, Brian. You've done a tremendous job here. We're going to go ahead and wrap up. Before we do, Tim, would you like to add anything?
Yeah, I think I do think there's a huge opportunity within the department to implement these technologies. And I think both of these projects have really provided a lot of really helpful results and information that we should take and work toward developing additional capabilities, but also deploying this technology more widely. And thank you, Brian and team, for another successful project.
Great. Thank you, Tim. Just a few quick reminders before we let everybody go. Our next webinar is early next year. It will focus on DoD-funded research efforts to develop technologies for treating soil and groundwater impacted by 1,4-dioxane. Please visit the SERDP and ESTCP webinar webpage to register for this and other webinars. I'd like to remind you, as Tim mentioned, that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can take a moment to complete the very short survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.